Welcome to The Explainer. Today, we're tackling a classic problem. How do you find a clear, clean signal when it's buried in a ton of noise? Well, we're going to dive into a really powerful technique called smoothed spectral analysis, or SPA for short, using material prepared by Dr. Nima Medallion. Okay, so here's how we're going to break this down. First, we'll get a handle on what's called the black box problem. Then we'll look at a really common first attempt to solve it and see why it totally falls flat. After that, we'll unpack the elegant solution that is smooth spectral analysis. And the best part, we'll see how all this cool theory boils down to just a few simple lines of code. All right, let's start with the big picture. Imagine you have some kind of system. It could be anything, an electronic circuit, a biological process, you name it, but you can't see inside. It's a black box. Our whole mission is to figure out what it's doing, but the only clue we have is its output. And that output is, well, it's messy. It's full of noise. So here's the basic setup. We're in control of the input, right? We send it a signal that we know. That signal goes into our black box, our system, which does something to it. But what we measure on the other side isn't just the system's clean response. Oh no. It's been contaminated by all this random, unpredictable noise. So the real challenge is, how do we separate the truth from all that static? The core philosophy behind SPA is actually pretty brilliant. It's all about changing your perspective. Instead of trying to fight with this messy, jumbled signal in the time domain, second by second, we shift our view. We pop over to the frequency domain. And this is where the magic happens. See, random noise, by its very nature, tends to cancel itself out when you average it. But the system's true behavior, that's persistent. It's a strong, steady signal that starts to shine through once the noise fades into the background. Okay, so before we get to the elegant solution, let's talk about the most intuitive one, the one everyone tries first, and let's see why, in practice, it's, well, pretty much useless. So you might be thinking, hang on a second, if the output is just the input multiplied by whatever the system is, can't I just, divide the output by the input to find the system? It seems so simple, right? Especially if we do it in the frequency domain. And you know what? That's a totally logical thought. This direct approach even has a fancy name, the Empirical Transfer Function Estimate, or ETFE for short. And on paper, it looks like it should work perfectly. And here's the reality check. This graph says it all. The ETFE, that jaggedy gold line, is just a chaotic mess. It is completely swamped by noise. The real system, that nice smooth blue line we're looking for, is totally lost in there. And what's really frustrating is that throwing more data at the problem doesn't help. The variance, the noisiness, it just doesn't go down. The noise always wins. This approach is, for all practical purposes, a dead end. Okay, so the direct approach is a bust. Clearly, we need a more robust method. Instead of just looking at the raw signals themselves, we need to get a little more sophisticated and start looking at their statistical properties. We need to look for averages and patterns. So our first major tool is something called the power spectrum. The best way to think about it is like a signal's fingerprint. It doesn't tell you what the signal is doing at any one moment in time, but it gives you a complete breakdown of its energy. It tells you, for every single frequency, how much power does the signal have right here. And how do we get this power spectrum? Well, first, we take our signal and do a Fourier transform to get into the frequency domain. But then, and this is the crucial part, we apply some kind of smoothing or averaging process. This is our first real step in taming the noise and reducing that wild variance we saw earlier. Okay, so if the power spectrum is a single signal's fingerprint, our next tool, the cross spectrum, is all about relationships. It takes two different signals, in our case, the input and the output, and compares them. For every single frequency, it asks a simple question. When the input zigs, does the output zag? Do they move together? Are they correlated? It reveals their shared dance moves, so to speak. What makes the cross spectrum so powerful is that it's not just looking at the input by itself or the output by itself. It's combining information from both to uncover their shared dynamics, the fundamental cause and effect relationship that's hiding underneath all that noise. So now we can put our two tools together, and we get this beautiful, simple core equation for SPA. Our estimate of the system is just the cross spectrum divided by the input's power spectrum. Think about what that means. We're taking the measure of how the input and output move together, and then we're basically normalizing it by the strength of the input signal itself. It's an incredibly elegant way to isolate the system's behavior. And get this, the method is so cool, it doesn't just find the system for us. It can also tell us exactly what the noise looks like.
All we have to do is take the total power of our measured output and subtract the part that we now know comes from the system. Whatever is left over, well, that has to be the noise. We're characterizing something we can't even measure directly. Now, why bother looking at the noise? Because analyzing its spectrum is absolutely crucial. It tells us if we're dealing with white noise, which is nice and random and flat across all frequencies, or if we have colored noise. Colored noise is trickier. It has a specific shape or structure. And if we don't account for it, it can actually fool our analysis and bias our results. So understanding the color of our noise is key to trusting our final answer.
All right, so we've been throwing around words like smoothing and averaging a lot. This is probably the most important step in the whole process, and it brings us face to face with a classic engineering trade-off.
So the formal way we do this averaging in the frequency domain is by using a mathematical tool called a frequency window. You can picture it like a little lens or a filter that we slide across our noisy data. By averaging the points inside that window, we smooth out the jagged peaks and valleys and get a much cleaner, more stable picture of our system.
And this brings us to the absolute heart of the matter, the bias-variance trade-off. This seesaw is the perfect analogy. On one side, if you use a really wide window, you'll get a beautifully smooth result that's low variance. But you might blur out some of the sharp, important details of your system. You've introduced bias. On the other side, you could use a super narrow window. Now you'll capture every tiny little peak and valley. That's low bias. But your estimate is going to be noisy and jumpy again. Finding the right balance on this seesaw isn't just a technical detail. It's the real art of signal processing. You have to ask yourself, what am I looking for? A single sharp frequency or the overall trend? Your answer determines how you balance this trade-off.
Okay, I know that was a good bit of theory, but here's the best part. Let's see how all this powerful, complex thinking boils down to just a few surprisingly simple lines of actual code. Seriously, in practice, this whole thing is just 4 steps. Step 1, prepare your data, usually just detrending it. Step 2, use a standard built-in function to calculate those spectra for you. And then steps 3 and 4, you just plug your results into those 2 simple equations we already learned. One for the system and one for the noise. That's it. It's incredibly straightforward. And just to connect the dots, each of these lines of code maps directly back to the concepts we've been talking about. Dtrend is our data prep. CPSD, that's the workhorse function that does all the heavy lifting of the spectral calculations for us. And those last 2 lines? They're just a direct one-to-one implementation of the core STA formulas. It's theory made practical. And just like that, we've completed the journey. We started with that raw, unusable estimate that was completely buried in noise, and by applying the power of spectral analysis and smart smoothing, we've transformed it into a refined, clear insight. We now have a solid understanding of both our hidden system and the noise that was trying to obscure it. So by embracing this core idea that sometimes you have to change your perspective and look in the frequency domain to find the real story, it really leaves you with a final question to think about. By smoothing away the chaos, what hidden dynamics, what clear, compelling stories are just waiting to be uncovered in your own data?